Ee, Merhaba arkadaşlar. Ne kaldığımız yerden devam edelim. Evet, şimdi diferansiyel denklemimizi yazdık. So the temperature changes at a rate proportional to the difference of the temperatures of the surrounding and the object. Okay. Of course, this gives us what? This gives us a separable equation, right? dt over 20 minus t is equal to r times dt, right? Separable equation, right? This is a separable equation. And then we just integrate both sides and we get what? Logarithm of 20 minus t is equal to rt plus a constant. Actually, I have two constants from both integrals. One from each integral, but they add up to one arbitrary constant. So I have this. And from this we get what? 20 minus t is e to the power, actually absolute value of this is e to the power rt plus c. And from this 20 minus t is plus minus e to the power c times e to the power rt. And from this again, tt is equal to what? 20 plus minus e to the power c e to the power rt. E to the power c is a positive number, but you have both signs in front of it. Therefore, I can just write it as follows: 20 plus constant times e to the power rt. And here c is just an arbitrary constant and r is proportionally constant, so it's again a real number, but most probably it's a positive real number because it's a proportion. Okay, now I have two constants to determine, and remember that we have two datas, right? Initial conditions. So I will use both of them to determine both R and C. All right, let's see. First one was this. At time 1 a.m., the temperature of the body was 30 centigrade Celsius. Right? No, it was 35. Sorry. Sorry, 35. And T of 2 is 30. Okay, so let's plug both of these values. So 20 plus C times e to the power. When I plug t equals 1, we get e to the power r. This is 35. And the other one is 20 plus c times e to the power. I put 2t, so t equals 2, so you get 2r, and this is 30. All right. And from this, we get what? Okay. Yeah, so c times e to the power r is just 15, right? C times e to the power r is just 15. And if I plug it here, 20 plus, this is just c times e to the power r times e to the power r, which is 30. So if I plug 15 here, so we get 20 plus 15 e to the power r is 30. And from this we get 15 e to the power r is 10, and e to the power r is just 10 over 15, so it is just 2 over 3, and r is just logarithm 2 over 3. Okay, and it's a yeah, negative number, I guess. Right, it's a negative number. Pozitif çıkmayacak mıydı? Yanlış mı yaptık? C times e to the power r 15, öyle yaptık. 10 bölü 15. Ha, o öyle yapsaydık olabilir. Tamam, neyse, sorun değil. Ama hani şu o zaman tabii pozitif olmak zorunda değil. Ha, ben şey yaptığım için burada evet. Neyse, sonunda zaten ortaya çıkar, doğru mu yapıyoruz, yanlış mı yapıyoruz. Peki, C'yi bulalım. Şimdi E üzeri R 2 bölü 3'tü. C çarpı E üzeri R 15. Ama E üzeri R de 2 bölü 3. 2 bölü 3 E üzeri R 15. Dolayısıyla E üzeri, pardon, ne yaptım? C çarpı E üzeri R. E üzeri 2 bölü 3 eşittir 15. Dolayısıyla buradan da C eşittir 45 bölü 2. O halde ne elde ettik? So TT is what? Neydi bu? Evet, bakalım. dt over şeyini integralde, bakayım orada yanlış mı yaptık? Evet, bunun integralini alırken değil mi? Negatif gelmesi lazım. Orada hata yaptık. T eksi şey ya. Dolayısıyla evet, şurada eksi var. Yani artı olacak. C'ye eksi koymaya gerek yok da şöyle eksi artı eksi, tamam. Şurada eksi var, eksi var, eksi var, eksi var, eksi var. Eşittir eksi, böyle oldu. Evet. C'de bir değişiklik yok galiba. E üzeri eksi R çarpı C 15. E üzeri eksi R yine 2 bölü 3. Tamam. Burada bir sıkıntı yok. Şimdi TT neydi? TT şuydu. 20 artı C çarpı E üzeri eksi artı. So this is 20 plus C times e to the power minus RT. Okay. O halde C değişiyor mu? Değişmiyor gibi geldi. Değil mi? C değişmiyor. Yani yanlış yapmıyorum diye düşünüyorum ama Şimdi farkını aldığımızda bunun yok. Şuradan bunu buraya attık. Şöyle e üzeri buradan da böyle yaptık. Bunun yerine 15 koyduk. R eksi ln 2 bölü 3 çıktı. E üzeri eksi R 2 bölü 3 hala. C çarpı 2 bölü 3 15. C böyle çıktı. Tamam. Şimdi bu 20 artı 45 bölü 2 e üzeri eksi R bölü T. Eksi R de logaritm, yani bu T çarpı logaritm 2 bölü 3 değil mi? Çünkü eksi R logaritm 2 bölü 3. Bunu da şöyle yazabiliriz aslında. Bu 20 artı bu logaritm 2 bölü 3'ün t'inci kuvveti. Dolayısıyla bu 45 bölü 2 2 bölü 3 t olacak. Evet. Tamam. Ee, evet. Bakalım mesela koşulları sağlıyor mu? Check yapalım. Şöyle. T1 neydi? 20 artı 45 bölü 2 2 bölü 3'ün birinci kuvveti, yani 2 bölü 3. Bu da ikiler gitti. 15, 35 çıkıyor. Tamam. T2 20 artı 45 bölü 2 2 bölü 3'ün karesi. Bu da ne olacak? 20 artı bu 4 bölü 9 olacak. Neyse şöyle yazayım. 4, 9. Buradan 2 geldi. Buradan 5, 10 etti. 30. Tamam, doğru yapmışız. Zaten dikkat ederseniz if we take limit as t goes to infinity, yani zamanı sonsuza götürürseniz ne olacak? O normalde vücut sıcaklığı 36,5'tu. Normally the body temperature was 36.5, but as time passes it will cool down and reach the temperature of the surrounding environment, right? Its surroundings, which is 20 degrees. And if you really take t equals infinity, t'yi sonsuza götürürseniz burada logaritm bu negatif değil mi? This negative number e to the power minus infinity, which is 0, so you get just 20. Limit tt as t goes to infinity is just 20 degrees. Okay, so this is the correct function tt. Let me write it one more time. 20 plus 35 over 2, no, 45 over 2, 2 over 3 to the power t. Okay, we would like to learn the time of murder. At the time of murder, at the time of murder, say at T0, the temperature must be 36.5 degrees Celsius, right? Hence, we have this equation. T of T0 should be this, and from this we get what? 20 plus 45 over 2, and 2 over 3, T0 is 36.5. And from this we get, okay, 2 over 3 to the power T0 is equal to Burası ne oldu? 16,5 20 çıkarttık. Bölü 45 bölü 2. Yani çarpı 2 bölü 45. 16,5 2 ile çarptık. 33 mü eder? 33 bölü 45. Yani 3'e bölersek 11 bölü 15 edecek. T0'yı nasıl buluruz? Logaritmayı alalım. T0 çarpı ln 2 bölü 3 eşittir ln 11 bölü 15. Buradan T0'da nedir? Ln 11 bölü 15 bölü ln 2 bölü 3. İkisi de negatif number. Dolayısıyla bu pozitif bir sayı olacak. Yok. Bu pozitif bir sayı çıkıyor. Evet. Yani gece yarısından sonra o zaman bulunmuş. Değil mi? Bilmiyorum, hesaplayabildiniz mi? Var mı hesap makineniz? T0 nedir? Negatif olsaydı şey olacaktı. Hani gece yarısından önce olurdu. Çünkü zaman 12'de 0 olarak alıyoruz. Pozitifse birden küçük bir sayı olacak muhtemelen. Evet. Dolayısıyla bu time of murder. Hesaplayabildiniz mi? Var mı hesap makineniz? 0,45 oluyormuş. Tamam. Teşekkür ederim. T0 0,76. Ha, 0,76. Ha, yani tamam, anladım. Şöyle bulmuş arkadaşınız. Çağdaş. Çağdaş'tı değil mi? Evet. Evet. Neredeydi? Ne yapıyorum? Hı, okey. 0,76. Yani biz de olsaydı saat 1 olurdu. Onun 1/4 kadar az. Dolayısıyla yani ne demek bu? 0,45 değil mi? Gece yarısını 45 dakika geçe. Okey. Sorusu olan var mı buraya kadar? Any questions so far? Okay, so let me start a new topic then. This is 2.4 differences between linear and nonlinear equations. We will state existence uniqueness theorems for both linear and nonlinear equations, and we will see the differences between the statements, and I will also give some examples how we can actually employ those theorems and so on. First, let's see a theorem for linear equations. Consider the first order linear ordinary differential equation, which is just this one, y prime plus pt Okay, pty equals qt. If pt and qt are continuous on some open interval I, which is given like this, let's say alpha beta interval containing a point t0, then for any y0, the initial value problem hangi initial value problem? Şu initial value problem. Denklemimiz bu. Y prime plus pty plus no equals qt, and the initial condition is this. At t0, the value of this function must be y0. And what is y0? Y0, any number you pick. Okay, any number you pick. This initial value problem has a unique solution. Y equals, let's say, phi t. Okay, defined on the interval I, which is alpha beta. Okay, now let me explain what's going on. Say this is the time interval and this is the y interval. I have some interval alpha beta, and my coefficient functions, both p and q, are continuous on this interval. Okay, on this interval alpha beta, both of them, and I am given any number t0 here in the interval and any value y0 here. Okay, so I have this point t0 y0, and what this theorem tells us that as long as p and q, the coefficient functions, are continuous for any choice of t0 in the interval alpha beta, and for any choice of y0, there is no condition on y0, it can be anything, the initial value problem has a unique solution. So there is a function uh, defined on the interval, let's say something like this. Okay, y equals phi t, and this phi t satisfies both the differential equation and this condition. In other words, so phi prime t plus pt phi t equals qt for all t in alpha beta, and phi t0 equals y0. Okay, so the theorem tells us that there is a function phi t which satisfies the equation and the initial condition, and this function is unique. There is exactly one such function. Okay, uh, that's why this theorem is called existence uniqueness theorem. Okay. Okay, let me write here. This theorem is called the existence uniqueness theorem for first order linear equations. Doing this theorem is easy. Actually, we have no, I shouldn't say that. Existence part is easy. We have done that. Given this differential equation, we solved this equation, right? We found an integrating factor, and using that integrating factor, we obtained the solution. But for the uniqueness, I didn't say anything, right? So let me write that thing down. Recall that we proved the existence part of the above theorem uh, using integrating factors. However, we didn't say anything about the uniqueness part, uniqueness statement. Gözüm var ama niye bir tane var? O konuda bir şey söylemedik. Onu birazdan söyleyeceğim. This theorem is very important for both, theoretical parts of the mathematics but also for actually our practical life. Why is that? Well, many things in nature and also many systems we build, like electric circuits, machines, anything you can think of relies on differential equations. They are governed by the differential equations. The systems works according to differential equations. And if we didn't have uniqueness part of this theorem, this would mean the following. You set up a system which is governed by some differential equation, and whenever you start the system, you set up some initial conditions and system works accordingly. If we didn't have this uniqueness part, that would mean that each time the system would work randomly. I mean, it doesn't have to start or work the same way, even if the initial conditions are the same. So one day it will work in one way, and the other day it will work in a completely different way. Okay, that would be the case if we didn't have this uniqueness part. That's why the uniqueness part and also the existence part have very practical importance for our actually world, not only the systems we build, but for also many other systems in the nature. Okay, because many systems are governed by differential equations. Okay, so this is the story for linear equations. So life is kind of easy for linear equations. We have always a solution, and the solution is valid on any interval as long as the coefficient functions p and q are continuous on that interval. But for the nonlinear equations, the story is quite different. The story for nonlinear equations is quite different. Let's state the theorem. Existence uniqueness. Theorem for first order ordinary differential equations. So this also includes linear case, because any linear equation is also a first order, ordinary differential equation. So this theorem is for all equations, linear and nonlinear. But in case of linear equations, our result is stronger. We will see that this result is not as strong as the previous one, because if you consider all the equations, then you cannot make strong statements. For special equations, you can make stronger statements. All right, let me state the theorem. Okay, consider a first order. Consider the what initial value problem. Below. Şöyle, y prime equals xy. Since it is nonlinear, I will use the variables x and y. Y is the dependent variable, and x is the independent variable. And let's say I have the initial condition y0, x0. assume that uh, there is a rectangle R, so that x is between alpha and beta, and y is between gamma and delta. So that the point x0, y0 in this rectangle. So initial condition is given in this rectangle. In other words, x0 is between alpha and beta, y0 is between gamma and delta, and both fxy and the y derivative of this function are continuous. So f is differentiable with respect to y. Moreover, this partial derivative is continuous. Continuous on rectangle R. Now, what is the conclusion then? The conclusion is the following. Uh, well, okay. Somehow I lost my notes. Let me just check from here. Okay. Uh, then there is a unique solution. Uh, y equals again, let's say phi x to the initial value problem above, to the above initial value problem. But this initial value problem is not necessarily defined on the whole rectangle. Defined on some interval, something like this: x0 minus, let's say, h, x0 plus h, for some h positive. So first, look on this theorem. Tells us that there is not much difference between this theorem and the theorem I stated for linear equations, but actually there is a quite a big difference. Let me explain that. Okay, so now here I have my interval alpha beta and interval gamma delta. So our rectangle is this. So this is our rectangle R, and I have x0, y0. Initial condition is given at this point. And this theorem tells us that there is a unique solution. There is a unique solution of this initial value problem. So there's a function phi x which satisfies this equation and this initial condition, but it is defined only on some interval containing x0, and we don't have a control on the size of this interval. So there is some h, okay, we don't know how big it is. So this is x0 plus h, this is x0 minus h, and on this interval I have a solution. Okay, sorry, I have a solution like this. Even though my coefficient functions were, you know, continuous on the whole rectangle, the solution may not be defined on the whole rectangle. It can be a very small interval containing x0. But the nice thing is that there is always an interval like this. It might be very small, but there is always an interval. Okay, so this is y equals phi x solution. Okay, it satisfies the differential equation. So when I plug it into the equation, I have this, and when I plug x0 here, I get y0. Okay, so the difference between the two type of problems. One of them is linear, the other one is nonlinear. In the linear case, as long as p and q are continuous on an interval, you would have a solution defined on the same interval. Okay, but here you don't have that. Okay, let me make an example. Yeah, I mean, it can be the case. Well, usually, of course, if the coefficient functions are not continuous, you cannot guarantee that even the equation has a meaning outside that interval, but it can be the case. But the theorem just doesn't guarantee that, okay? It just guarantees that there is a small interval on which the solution exists, but in general, we cannot even control the size of the interval. Now I will show you some examples, some examples why this is the case. I say proof here, but I am not going to prove this theorem. By the way, I should tell you that this theorem, the proof of this theorem is not easy actually. You will see the proof of this theorem in Math254. So you need to have a lot of real analysis knowledge to prove this theorem. The existence part of the linear version, linear equation version is easy, and we have done that. Because we just wrote down the solution, right, using the integrating factor. But this theorem, the proof of this is not easy. I can only give you a sketch of the proof. Maybe I should, in the remaining 8 minutes. And next time, I will give some examples related to these theorems. Okay, sketch is this. Now we consider this equation. Y prime is equal to fxy and y0 equals y0, right? We would like to solve this equation where x is between alpha and beta and y is between gamma and delta. All right. First, we convert this to an integral equation. Convert this to an integral equation. By the way, you can find actually the proof of this in my videos, Math349 videos on my web page. It should be towards the end of the semester, okay? Just you may watch my Math349 videos. Okay. So first we convert this to an integral equation. How can we do this? Well, we do it this way. Y of x minus x0 is equal to what? This is nothing but integral from y0 to x, y of t, y prime t dt, right? First fundamental theorem of calculus. And what is y prime? Well, y prime is just from the equation f of xy. So instead of x, I use t, and then here I have y. Of course, y has x in it, therefore t in it. So I have this. So from this, we see what? Y of x is equal to y of x0 is just y0, and I take it to the other side. So I have y0 plus integral from x0 to x f of t yt dt. And if you take derivative of this with respect to x, you will get back to the original differential equation. So this integral equation is equivalent to our initial value problem. Okay? And then you solve this equation next we solve the integral equation. Let me, so this equation, which is a large value problem. How? Well, we use so-called Picard's iterates. The idea of Picard's is the following. You see, I have y here and y here, so it is not easy to solve. What Picard did, he regarded these two y's as different y's. How? He built up some functions, form a sequence of functions. Well, okay, y equals phi 0 of x is the constant function y0, the constant function. And then let y equals phi 1x to be this expression, y0 plus x0 to x f of t. I will put y here, but for the y, I'll use phi 0, not phi 1. So phi 0 x, phi 0 t dt. And keep repeating this. Similarly, let y equals phi n x to be just this expression, y is the integral from x0 to x f of t, and then here I will put n minus 1 t dt. So inductively I can build this sequence, okay? And then you so we obtain a sequence of functions phi and t, phi and x, sorry. And then you show that finally we show that this sequence converges to a solution, and the solution is and one proves that the solution is unique. Well, all these things requires, of course, a lot of proofs, and it is done in that course, real analysis course. You have to build up this sequence. You have to show that it is convergent. So let phi x to be the limit of this, okay, as n goes to infinity. And then if you take the limit of both sides here, right, I have phi n x, sorry, phi n x, what was it, y0 plus x0 to x f of t phi n minus 1 t dt. You take limit as n goes to infinity, this goes to phi x, and then I have x0 to x, I have t. What is the limit of phi n minus 1? Of course, that will also converge to phi of t dt. Hence, this phi t solves the, hence phi x solves the integral equation. And this is the proof. Of course, this is just a sketch. There are many things you have to prove here. Why this limit exists, and why the whole process gives us a unique solution. All these things has to be proved, and it requires almost everything done in the real analysis course, Math 349. Okay, so this is just a sketch, but this is the basic idea. All right, let me stop here. So tomorrow I'll do some examples explaining the two theorems, how we use them, and so on. And then we will pass to, I guess, exact equations. Yeah. All right, let me stop at this point.